Welcome to ePathshala lecture series in computer science. This is a course in cloud computing. Today we continue our discussion on virtualization. So, the learning objectives of today's module will be, we will look at what is a virtualizability, the ability to virtualize a system. We will look at the proposers of this virtualizability theory. They are two authors of a paper, Popek and Goldberg. They proposed a theorem. We will look at that. We will look at a very popular ISA x86 architecture, and we will see that why the question of virtualizability is arising, and we will also see how to work around such problems and look at the possible methods of virtualization, followed by summary. So, in the last class we looked at the virtualization, the types of virtualizations and the types of virtual machines, and this class we will look at these objectives. So, specifically we will talk about CPU virtualization or HAL virtualization, abstraction, hardware abstraction layer virtualization. There are a few points that we need to understand, that we can emulate a physical environment in software. So, a software can behave in a similar manner that like a physical environment, and therefore can allow a program that is written for a different hardware to run on a different hardware. We will talk about this emulation process. Emulation is a very important aspect of CPU virtualization. It provides that software can provide an environment which is completely similar to the hardware environment, although there is no specific hardware environment for that particular hardware, but processes that are written for a specific hardware can run on this software emulation. This creates the capability of running another operating system inside a second operating system. Even it creates the environment for running two operating systems on the same hardware. So, is virtualization same as emulation is a question that we need to address. Let us look at what is emulation. Emulation is a very commonly used mechanism. This is what emulation does. We have a physical hardware which is maybe say ISA, some ISA. Now, I can emulate another ISA. ISA 1 is different from the host ISA, and I have the guest ISA which is ISA which requires ISA 1. So, this simulation layer is emulating in the software the physical hardware of ISA 1, but it is running on this particular ISA which is different from ISA 1. Similarly, if this is not ISA 2 either, then this emulation layer will emulate in software the behavior of ISA 2, although it is not running on ISA 2, and this guest of ISA 2 will interact with this emulated environment, and this emulated environment in turn will interact with the physical ISA. So, how to implement such an emulation? There are certain techniques, but the most important or most popular technique is called interpretation. So, what is interpretation? Every instruction that happens in the guest will be caught by the emulation environment, will be translated according to what is required in the physical environment and will be executed. Just like a normal interpretation, one instruction at a time, the guest will issue an instruction, it will be caught or trapped by the emulation, the software emulated environment, and it will be translated according to the physical ISA on which it is running, and it will be run. It is a very tedious process to have a emulation method by interpretation. So, if it is not interpretation, and if interpretation is not really required, then what we can do is we can go for a binary translation. So, what happens in a binary translation is a bunch of instructions of the guest can be looked into by the emulation environment, and they will be converted to the hardware specific ISA code, and the whole of the guest will be converted to the new ISA specification code, and then it will be run. Obviously, binary translation works better than interpretation. But is that what is good enough? We do not want to emulate the whole of ISAF to another ISA. What is actually required in a typical cloud environment is that I allow one operating system to run on a hardware meant for that operating system. So, an operating system and ISA tie bonding we are not breaking. We are allowing the operating system and the ISA to be bonded, and we have one ISA. The operating system of this ISA is running. I want another operating system for the same ISA to run on the same hardware. So, emulation is not really required, and therefore, this method mechanism is called virtualization. In virtualization, we have only one ISA. This virtualization layer is interacting with that ISA, and this OS is meant for this ISA, even this OS is meant for the same ISA, but we are giving the system the ability to run two operating systems at the same time. So, this is not emulation, this is virtualization, where we have the same target ISA as the operating system, but we are bringing in the ability to run multiple operating systems in our environment to make an envelope out of our applications and a different operating system and run it on top of a hardware. And these envelopes are called virtual machines, and as soon as we put these virtual machines, our application operating system combination in an envelope called a virtual machine, we get many advantages of running these virtual machines on different machines or on the same machine, and that is what we will look at. We already saw that these virtual machines can be migrated, can be put to rest, can be brought back, can be suspended. All these advantages happens when we have a virtualization technique. So, what are the requirements of a virtualization? We want the guest to have near native behavior. What does near native means? It means that we have the hardware, and this hardware, that the ISA and the corresponding hardware, the guest that we are running, the VM or virtual machine that we are running, the virtual machine should be running through the virtualization layer on top of the hardware in a manner that will be equivalent to running it directly on the operating system and the hardware. So, that is called a near native behavior or the native behavior, but we can't have a completely native behavior, but we can have a near native behavior. That is the requirement of a virtualization. So, since the ISA is the same, so running two different operating systems should simply be a scheduling mechanism. So, we need to manage the execution, which operating system should run when. If we manage that, then perhaps it would be perfectly fine to run two operating systems on the same environment, on the same machine, but unfortunately it is not that simple. So, let us look at why the ability of a VMM needs to be more than just simply being a scheduler. So, let us talk a little about today's computer. Today's computer are basically the same, follow the same mechanism as the third generation computers. We looked at the third generation computer. These are the IC, integrated circuit based computers in the area in the time of 6471, that time. There was an operating system. So, an operating system was running on top of the hardware. Applications were concurrent in our third generation computers. So, different processes can be run on the same hardware, and in this generation of computers we had a dual mode CPU. What is a dual mode CPU? Dual mode CPU has two different modes. One is called the privilege mode and the other is called the user mode. Now, OS runs in the privileged mode. So, whenever OS is running, the OS runs in the privileged mode, and whenever the user process is running, the user process runs in the user mode. So, in dual mode operating system, we have the advantage of running certain instructions only by the operating system. We will just now look at that. So, when a user process is executing, we have a specific set of instructions. Those instructions can be run in the user mode of the CPU. So, the CPU user mode can run a generic set of instructions, but whenever an OS process is executing, this generic set of instructions can still be executed, plus there is a special set of instructions which will also be executed by the CPU, because the CPU is running in privileged mode. So, OS can run everything that a process can run. In addition to that, OS can run a set of additional special purpose instructions which interacts with the devices, which does so many additional work on behalf of operating system in the CPU. So, whenever that kind of work is required, the OS has to take care of this. But will it always work? What happens if a user process wants to execute a special instruction? The user process wants to send a data to the hard disk, the user process wants to print something in the monitor, the user process wants to interact with the timer. So many, on different occasions, the user process will want to interact with the other devices. So, what happens to that? But these are the instructions that the user process in the user mode of CPU cannot run, only OS can run. So, what will happen? As soon as a user will try to execute such a special instruction, the CPU will immediately convert to the CPU, the privilege mode, and there will be an OS process that will be brought in, and that OS process in the privilege mode will run those instructions on behalf of the process which wanted to run. So, therefore, whenever we must have seen in operating system that whenever a process wants to bring a file from the hard disk, wants to interact with another process running in the system, for all these it has to generate what is known as an interrupt. So, generating an interrupt is nothing but calling the operating system to help with the change of mode. So, as soon as the user process running in the user mode of CPU wants to execute something special, it has to execute a system call. It has to ask the OS to come in, and it has to execute that specific instructions. So, this method of calling the operating system using a system call, or if some other operating system gives another mechanism to knock at the door of the operating system, this is called trapping to operating system or trapping to OS. So, what happens when we have trapping to OS? User mode instruction traps whenever it has IO operation or any other special action, the CPU mode is changed to privilege mode and operating system specific routine is executed. That operating system specific routine will execute the instruction on behalf of the called process, and whenever it is over, the respective result is sent back to the specific process which has been calling. So, in this scenario, how things will work? This is the traditional OS. The traditional OS has the layered approach. So, let us look at the layers once more. So, we have the hardware layer, and then we have the operating system layer, and then we have the application layer. So, when normal application instructions run, they are executed by the hardware. So, the application running any normal instructions, it runs on the hardware directly. So, native speed. It is the CPU is in the user mode. When some special instruction is executed, the application has to trap to OS. So, trap to OS happens, and the application cannot run that instruction directly on the hardware. It sends that instruction by trapping to OS to the operating system. The operating system has a special set of routines. The operating system in turn will execute it on the hardware. So, when we have anything that the application directly cannot do, we have to trap to the OS, and the OS will do the work. So, this time the CPU will run in the privilege mode and will allow the operating system to do it. Now, if we have a VMM or a virtual machine monitor or a hypervisor, how do we manage this scenario? Let us look at this. Now, we have this operating system is a guest operating system, and we have one more layer which is the VMM layer. So, hardware, the virtualization, the hypervisor layer, guest OS and applications. So, the application and the hardware continues the same. We run the application generic instructions on the hardware directly. The same ISA, the application is meant for the same ISA as the hardware in a virtualization environment. So, therefore, there is no problem, it is possible. Now, what happens when it traps to the operating system? It traps to the operating system for the special instructions, but the operating system now cannot execute it directly on the hardware. The operating system in turn calls the virtualization layer or VMM or the hypervisor. The hypervisor will execute this according to the to its own mechanism. So, now we have added one more trapping to the application traps to OS and guest OS traps to VMM, and then VMM executes it. So, how the VMM should be implemented? The VMM will act as a scheduler, will allow multiple operating systems, but we have to look at the problems. What are the problems? What about the guest OSs? The guest OS is not aware of the existence of the VMM. They are not written. We must remember that operating system is a software. That software is written for running on top of the hardware. So, if the software has to trap to VMM, the simple mechanism is we rewrite the operating system. The good old operating system cannot continue, which is a very difficult task. So, that is one problem, and the other problem which brings us to the formulation of virtualizability is, unfortunately, not all hardware can accept this kind of change. Let us look at this. This is called the virtualizability. Virtualizability is nothing but the ability of a hardware or a machine to allow an operating system to run on top of the VMM. So, any VMM specific requirement needs to have three properties. These properties are equivalence or fidelity, resource control or safety, and efficiency or performance. Let us look at what Goldberg in their 1974 paper, they mentioned these properties and they defined what is virtualizability. Let us look at that. So, the equivalence property says that any program running on a VMM should exhibit the behavior identical to the one if it is running directly on the machine, at least near native. This is what we call a near native behavior. Resource control safety is that VMM must be in complete control of the virtualized environment, otherwise we cannot call it a virtualization mechanism. The third property of efficiency performance says that a statistically dominant fraction of the machine instructions must be executed without the VMM intervention. So, the application instructions should directly be able to, in the user mode, the machine should continue giving the allowing the applications to run the same instructions. So, what is Goldberg theorem? This is the Goldberg theorem actually was devised for IBM System 370 and Honeywell 6000, but it is still as we said that third generation computers are quite similar to today's modern computers, and therefore, we can have the same mechanisms working. So, the hardware consists of the processor and memory, and the processor can operate in two modes, and a subset of the instructions are privileged mode instructions, and machine addressing is done with the relocation. So, uniformly addressable memory, and memory can be addressed with a specific relocation register. With these constraints, this is what Goldberg has proposed. They say that for any conventional third generation computer, a virtual machine monitor may be constructed if the set of sensitive instructions for that computer is a subset of privileged instructions. Quite a few important interesting words, terms that are there. First is, this is for a conventional third generation computer. It does not worry us because we have shown that our today's computer is quite equivalent to a third generation computer. Next, it says sensitive instructions and privileged instructions. So, what are sensitive instructions and what are privileged instructions, we will have to see. And then it says that virtual machine monitor may be constructed if the sensitive instruction is a subset of the privileged instructions. So, this is the key part of Goldberg theorem. So, basically the instructions, they have divided into two parts. One is called the privileged instructions. We already saw what is a privileged instruction. There is another set of instructions which are called sensitive instructions, and these sensitive instructions are the ones which are going to make changes in the system, in the hardware. So, those are called the sensitive instructions. So, there are three types. One is the normal non-privileged set of instructions, which is the largest, and then there is a set of privileged instructions, and there is a set of sensitive instructions. According to Goldberg, a machine is virtualizable if its privileged instructions are a superset of the sensitive instructions. So, this is a virtualizable system where its privileged instructions are superset and sensitive instructions are a proper subset of the privileged instructions. This kind of machine where the privileged instructions are not a superset of the sensitive instructions, some part of the sensitive instructions are not privileged instructions, these kind of machines are not virtualizable. Let us look at the x86 architecture. In x86 architecture, this has a ring formation, and in the there are 4 rings. In ring 0, we run the kernel, and in ring 1, we run the we do not run anything, in ring 2 we do not run anything, and in ring 3 applications are run. So, 1 and 2 are idle, they are not in use. So, can we virtualize x86 architecture is what the question arises. So, let us look at the problems of x86 incidentally is the most commonly used architecture by Intel Corporation and others. So, most of our machines are based on x86 architecture. So, let us look at the problems. Some of the sensitive instructions do not trap. So, they are not the privileged instructions. So, the basic virtualizability condition of Popek-Goldberg is not accepted in our x86 architecture. Some of these sensitive non-privileged instructions, they fail silently, thereby causing a big problem. Such instructions that will even change the mode of the register or the system, and they will fail in the user mode without the CPU mode changing. So, therefore, according to Popek-Goldberg, x86 is not virtualizable. The second problem of x86, if there are 4 rings and OS is run in ring 0, that is the kernel, and applications are run in ring 3, then the VMM will run where? VMM is supposed to be running on top of the hardware. Here on top of the hardware, the kernel is running in ring 0. So, if VMM has to run on top of hardware, we have to run VMM in ring 0. Then what about the guest OS? Guest OS is used to running on top of the hardware and therefore in ring 0, but we cannot run both in ring 0. We have to make a choice. So, for being able to do that, what we do is we make a duplicate machine for a process. Machines have only dual mode. It can run in privileged mode and it can run in user mode. So, user mode will run the user process. Kernel will run in the privileged mode. Then VMM will run, it has to run in the privileged mode as well. So, how to provide this? The other alternative is I run user in the user mode, I run VMM in the kernel mode, but then I do not know where to run the guest OS. So, guest OS can either run in the user mode or in the kernel mode. We cannot run guest OS in the kernel mode. So, therefore, our only choice is that guest OS will run in the user mode. So, this is called deprivileging the operating system, and let us look at deprivileging. So, this is the usual operating system where we have the applications running in the user mode and OS running in the kernel mode. This is the deprivileged scenario where both the guest OS and the applications are running in the user mode. We divide this user mode into 2 parts. One is called the virtual user mode and other is called the virtual kernel mode, and VMM is run in the kernel mode. So, there are various methods of virtualization. By definition, the privileged state of virtual system differs from the underlying hardware, and the VMM's basic function is to provide the execution environment of the different operating systems. So, there are 3 techniques. One is called emulation. We already seen how emulation works. A second technique we will look at, which is called trap and emulate, and the third technique is called binary translation. So, to summarize today's module, we looked at the virtualizability, the ability of a hardware to do virtualization. We looked at the Popek-Goldberg theorem and saw what is virtualizability and what is required for virtualizability. We looked at x86 architecture and saw that x86 architecture is not a virtualizable hardware. So, we have to look at how to do it, and we saw that there are various methods of virtualization. In the next class, we will see these methods of virtualization and some specific cases. These are our references.